way because of the virus. So we're trying to make everything online as possible. So yeah, let's take a look at lab 4 and stay safe. Okay. So for lab 4, it's very similar to lab 3. So lab 3, we did simple linear regression. In that case, we considered one predictor. In this case, we're looking at multiple linear regression. In the case, we have multiple predictors, and this is more realistic because in practice, you often collect many variables, and sometimes you don't know which ones are useful. So you have to pick which ones are useful, and we'll talk about this later. So the data set we're talking about is called the river nitrogen. So basically it's dealing with how much nitrogen in the river and why this is causing this. Okay. So here there's a little bit of introduction saying that there's lots of different ways for the river to get nitrogen. For example, it could be getting it from the air, the rain, or like sewage and different human activities. Okay, did not cause Siri. Anyway, so basically we considered a few different, so the response we have here is NO3, which is the nitrogen concentration measured in mu m per L. And then we have these different source of nitrogen. So for example, the discharge. Also, we also have a few variables about the river. So if you look at the data, we have, I think, 42 different rivers in different countries. And for example, nitrogen is actually a parameter of the river. So it's the estimated annual average discharge of the river into an ocean. We also have runoff and area, both measuring the river and the density, how many people living along the density of the river. And then we have the nitrogen deposition. The depth is basically how much nitrogen is from the atmosphere. And then we have M precipitation, which is basically the concentration of nitrate in wet precipitation at sites located near the watersheds. And then we have precipitation, so how much rain it gets. Okay. So basically we have this one outcome, the response, NO3, and we have 7 possible predictors in this case. Let's take a look at the question. So first for question 1, so the design. Okay, so obviously this is an observational study, again, because we can't really manipulate any of this. So of course, maybe you can do, you can build like those models, like a micro world kind of thing. Like you have a river, you have human, you have animals, and you have all these kind of things. But in this case, it's real numbers from the actual world. So it's a pure observational study. And for observational study, we say that usually we can't make causal claim. For example, if you see that rivers from higher, oh my God, what? Oh no. If you see a river with high nitrogen concentration, you can't really be saying this is caused by, for example, precipitation or something. There are lots of things play in this big picture, and we only have part of the picture. Okay. So that's why here, for this question, we can't really use this to demonstrate that the higher nitrogen concentration in the river are caused by human activities. I mean, I'm guessing yes, but it's really hard to prove that it is caused by human activities because there are lots of natural activities too that can play a huge part in these things. Okay, and next let's take a look at the scatter plot. Okay. So again, I changed my number a little bit. Okay, in the data we have an extra variable called export. I don't think this variable is used at all in the whole study, and actually you can delete it if you don't want it. It's kind of yeah, I'll delete it. It's not really doing anything. I mean, for this homework. Okay. Okay, so for scatterplot, let's do graph chart builder, and then let's do scatterplot matrix, okay? And then we're going to put all 8 variables in the box. Oh God, it doesn't allow me to do that. Okay. Okay. Okay, perfect. 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. Let's take a look at this. Okay, so there's lots of information here, but mostly we're curious about the relationship between the NO3, which is also here because there's not enough room. So NO3 versus the predictor. So these 7 plots are the ones we're most interested in. It's kind of small, the plots, but you can see the main pattern. For example, for this guy, I see a pretty obviously kind of a linear pattern. It's not very strong, but it's pretty good, possibly linear. It's a little bit curved, but its main pattern is pretty linear. This one as well is pretty linear. This one is kind of decreasing, 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 but it's a little bit non-linear. Okay, so based on this, I would definitely see that some variables are related to the response. So that's a good start. But we do see some non-linearity. Okay, and that's why for the next question, for question 3, we're going to look at whether a log transformation is helpful in enhancing the linearity between the variables. So we're going to do log transformation for question 3, log transformation on all the 8 variables. It's a lot of transformation, okay, but let's do this. So I'm going to have to do this one by one. So transform compute variable, and then we do the first one. I'm going to name this line NO3, which is ln, come on, no, NO3, okay, and you do this 8 times, okay. I know it's a lot of work, but I think there are better ways, but I don't know. This is the only way I know how to change this charge. Okay, I am recording. Okay, that's good. Run off. Area. Density. Depth. NPREC. Nitrogen precipitation. Okay, we have the last one, precipitation. Okay, awesome. So if you check your data, you should see 8 new columns. Oh no, not this one. This one. Yes, perfect. And basically from now on, you won't be needing the original variables. We're going to use the log transformed variable from now on, okay? So for question 3, we're going to do 2 things. First, we're going to do this matrix scatterplot matrix again to see whether the transformation helps with the linearity. And then we're going to compute the correlation matrix to quantify the correlation we see, okay? So let's first do the scatterplot matrix again. So chart builder, and then let's remove all of these, and then we're going to select the one. Oh, the software is so useless. Okay, I'm missing this one. Okay, and again, we're mostly interested in these ones, okay? And you can see that some of these are much better than before because, for example, for this one, it looks pretty good. So the log density and the response are pretty linear related. And we have this one is pretty good, linear, pretty good, non-linear. These 3 are not very strong, and we have outliers, but it's better than before, okay? And then let's do the scatterplot matrix, the correlation matrix. So analyze, correlate, bivariate, and then we are going to use the log transform variable. Okay, so you have a matrix, okay, here, and again, we are mostly interested in the correlation between the y and the x. So these guys, you see that density has a pretty high correlation, 0.86, and then some of them pretty high log deposition, and nitrogen precipitation are both pretty high, and then we have negative ones, okay. So here it also asks for one more thing, whether collinearity is a problem. So what is collinearity? As you can see from the name, it means something are collinear. So often when we're doing regression, we want the predictors to be different in the sense that we want them to be contributing in a different way. So we don't want the predictors that are highly correlated to appear in the equation. So if these do happen, we call it a collinearity, and it's something we don't want to happen. Okay, so how do we diagnose this? Basically, you look at the correlation between the x variables. For example, between my log discharge and my log area, the correlation is really high, 0.85. So in this case, we see these two variables are too similar, and that might cause a problem in our analysis later. So if this happens, we have a problem of collinearity. And what's the threshold? Like, I don't have a magic number saying if it's higher than 0.8 or something, but it all depends on, again, sample size and also empirical numbers in a sense. But the correlation is a very, very rough number to look at. There are more sophisticated measurements you can take, but this is a starting point. Okay. Um, okay, and then let's look at question 4. Question 4 asks you to define the model. When they ask you to define the model, you basically just have to write out the equation. Okay, so and I will also put this file in the comment section in the video so you can find it there. So basically you can write it this way. So the response equals to, beta 0 plus all the betas, um, and then plus errors. So or you can write out as a conditional mean. So conditioned on all of these 7 predictors, you have and then you don't have to write out error term. So either one of them is okay. Okay. Um, okay, so, and then also the model assumptions. So for the model assumptions, we still have that line assumption. So linearity, which we already checked in scatterplot, independence. Uh, Here we don't have really a rigorous independence because all the rivers they're related. I mean, some of them are coming from the same source, some of them going to the same place, and it's a complicated problem. But on a broader sense, we're going to say it's independent. The normality and equivariance are both. We're going to check it using the residual plot and the PP plot later. Okay. And then for question 5, we're going to do a backward elimination. So like I said in the beginning, sometimes we measure so many things. We have so many variables and we don't know which predictors are useful. So we're going to do a thing called variable selection. So variable selection, aka basically selecting variables that are important. So how do we do this? There are different ways. So the most naive ways here, we're going to talk about including 3 ways. So forward, backward, and stepwise. Okay, so how does that work? Let's take a look at this figure. So for forward, let's explain backward first. For backward, so basically, let's say imagine we have 4 variables, we have 4 predictors to start with, and we want to pick some of them that are important. Okay, so how do we do this? So first, we go back, right? Go back. We run a model with 4 predictors, all of them, and if we look at the coefficient table, we see are all of them significant? If they are, we stop. But if, for example, if A appear not significant, and we basically delete backward elimination, right? We eliminate the variable that's the least significant, which means the one with the largest p-value. So for example, if A has the largest p-value, and we're gonna remove A, and we're gonna leave with B, C, D. And we do this, we keep doing this until we can't eliminate anymore. We can't eliminate means that everybody in the equation is significant, okay? So that's backward. Forward works the other way around. You start with nothing, and you kind of throw things in your bag. So first you have to consider which one do you put in your bag. So A, B, or C, or D. Basically, you put the one that's the most significant one. So aka the one with largest correlation with the response. So for example, if B has largest correlation, right, and you do and you put B and you do this one more time, you add from A, C, D to see which one is the most significant one, and you keep adding until the thing that you just added is not significant. Okay, so and stepwise basically is doing this as a hybrid of these two. You do one step of backward and then you do forward and backward, forward, backward, forward, and so on. Okay. So in this case, we're going to use backward elimination to do question 5. Okay, so we're going to put all 7 of them there to see which ones are selected. So let's do this. So backward elimination, we're going to transform, no, analysis, regression, linear regression, and again we're going to use the log transform variable. So we're going to put log NO3 as the response, and we're going to put all the other 7 as predictors, and we're going to do backward method. Okay, let's also do the pp plot and the residual plot. So residual plot is basically the z residual versus z predicted, and then we're going to do the normal probability plot, and then we're going to do okay. So let's take a look. So the first table gives you the order the variables were eliminated. So first we have everybody, and then log runoff were eliminated, log deposition, log precipitation, log area, log discharge. In the end, we are left with 2 variables, basically. I think so. Yeah, so the last model, the model 6 is my final model, and my final model has 2 predictors, density and precipitation, okay? So this is basically the order the variable were eliminated, okay? They ask you what's the estimated equation. So when they ask you what's the estimated equation, you basically plug in the beta values in your equation. So in my case, my final model would be, so here model 6 is my final model, which is, so the response, the log NO3 equals to 1.003 plus 0.4 times log density plus 0.2 times log M precipitation. That's my final model, okay? And what percentage variation you can get is from the R square. Okay, so again, we just look at R square, not, there's also adjusted R square, but we don't care about that in this class, so we're just gonna look at R square, okay? What's the p-value for testing the overall significance? Whenever they ask for overall significance, you're looking at the ANOVA table, okay? So because now we're dealing with multiple regression, so you have multiple betas to test. When we're talking about overall significance, we're basically saying the null hypothesis is that all the betas you have are 0, okay? So, and to check that, you have to look at the ANOVA table. So in this case, my ANOVA table might look at the final model. I have small p-value, which means some of my beta are not 0, okay? And then I move to my coefficient table. My coefficient table tells me that log density have a small p-value, so non-zero. My log and precipitation also have a small p-value, so both of them are significant, okay? So that's the individual significance. So again, overall significance, you look at the ANOVA table, and individual significance, you look at the coefficient table. And both of them are using 5% p-value, okay? So that's 5. So after 5, what do we have? We have used backward elimination to select a model, a very small model. That's good. We always want a very economic model, like, you know, it's small, but it's also powerful. A model with 2 predictors, log density and log M precipitation. And then for question 6, it's basically checking the 2 assumptions. So let's take a look at the QQ plot. The PP plot here, I would say it's not very bad, like the majority are still on the line. We have a little bit problem here, but I would say it's a small validation. And look at the residual plot. It's not perfect, right? You do see such a little bit of like decrease of, kind of like a decrease of variation, like it's kind of like a cone in this case. But I would say it's pretty random, like it's not perfect, but it's pretty good. Okay, it's 6. Okay, and then 7 and 8. So for 7 and 8, we're doing some extra square sum of square f test in a sense. Okay. Okay, let's move on. This part is really hard to understand, but let's just move along with the question. So if you look at 7a, 7a says the first step, we're going to do a forward selection to do a model. We're going to put 4 variables there, and then we're going to do the forward selection using these 4 variables, okay? All of them in log scale. So discharge, runoff, area, and precipitation. So let's run another model. So regression, linear regression, and then discharge, runoff, area, and oh my god, and precipitation rate. So discharge, runoff, area, precipitation. Discharge, runoff, area, and precipitation. Okay, and then we're doing forward. Okay, and let's do okay. So basically, the model stopped at the first step. Basically, it means after discharge, nothing can be added. So we have our final model, just a simple linear regression model with one predictor, the log discharge. The R square is about 13%, which is not very high. Okay. So basically here, it only asks you to report the R square. Okay. 7a. Yeah, R square. Okay. That's odd. Okay, for 7b. 7b asks you to obtain the case statistics. You guys probably haven't learned in class. All of these are measurements that help you to identify whether a point is an outlier. Okay. You can also take a look at the residual plot. In the residual plot, for example, in my case, this point is really bad because it's kind of out of bound in the x direction and also y direction. So let's take a look at which case is this. So if you right click on this point and you to show data labels, and this one is case number 3. So case number 3 is I think it's the Carra River in Ireland. Okay. And then you have to obtain these numbers about this point. Okay, so how do we do that? So you can let's run the regression again. So linear regression. We already know the model only contains discharge, so we can just do discharge here because that's the model we end up with using the forward selection, and we just do enter because we have done the selection part. And in the save option, we're going to save the studentized residual, the Cook's distance, and the leverage values. Okay, and then let's do continue and let's do okay. So now if you check your data and you highlight case number 3, you should have these 3 values, and that's what they want. Okay, come on Siri. And that's what they want. Okay, how do we use this value? So basically, if you have a studentized residual larger than 2, indicates an outlier. If you have a Cook distance larger than 1, it's an outlier. If it's leverage larger than 2p over n, p is 1 because we have one predictor over 42 sample size, it's an outlier. Okay. And now, the question asks you to rerun the model without the case. Okay, so we can redo the forward selection without the case number 3. And then for the next question, 7c and 8, we're going to also ignore case 3. How do we ignore case 3? There are different ways. One way I think I do data, and then I do select the cases. I do if condition river, because I know Carra River is not selected, so I'm river, and this is doesn't equals to quotation Carra ARAGH. Then I do continue and then I do okay. And if you check your data, you see this one is crossed out, so that's good. And now let's do the forward selection again. So for the forward selection, we do analyze regression, linear regression. Forward selection, we have discharge, runoff, area, and then precipitation. No, area, runoff, precipitation. Forward. And then let's uncheck these things because I don't want to save them again. Okay, and let's do okay. So, so the new model has a larger R square, 26%, which almost doubled as before. Okay, so the point is pretty influential. After removing one point, the R square increased a lot. Okay, as for part B, part C asks you to run a regression by adding, we're going to add deposition and the nitrogen precipitation into the model to see whether it improves the model. Okay, so we're going to run stated above the question about the association of NO3 as now an alternative. So basically we're doing an extra sum of square F test, and basically we're doing an extra sum of square F test, and you need to figure out what's your reduced model, what's your full model. So the reduced model is basically, when we're testing whether a few variables are significant, you want to do a model with these variables and without these variables. And the reduced model is basically without these variables, and the full model are with these variables. So in our case, in question 7b, we have selected discharge. So that's our baseline, okay? So the reduced model only include these one, and the full model include discharge, log deposition, and log and precipitation. The deposition and precipitation are mentioned here. That's why I added it here, okay? So we already have the output for the reduced model, and we just have to run the full model and then to get these numbers and plug in here. So you need, for each model, for the full and the reduced, you need two numbers. One is the sum of square of the residual, another is the degree of freedom of the residual, okay? So for example, this is my reduced model, and this is the sum of the residual, and this is the degree of freedom. These two numbers, okay, and we run the full model. So analyze regression, linear regression. We run the full model. The full model is discharge. That's like the reduced model, and we add two things we want to test. So the deposition and precipitation. Yes. And then let's just do enter, because we don't want to do selection here. We just want to do the model as it's stated. Okay, so let's do okay. So basically here from the ANOVA table, you have the sum of square of residual and the DF. This is the SS residual of the full model and the degree of freedom. And you basically plug all the four numbers here and calculate F statistics, and you get your test statistics, and then you find the p-value from the test statistics. You can either look at using the F table you guys have. In that case, you might only be able to get a range. That's okay. Or you can use an online F statistic calculator. You can find it in Google it. Okay. So that's 7C. For question 8. For question 8, we're doing. So here we're taking one more step. It's asking you whether the population density is significant or not. Oh, it's basically adding one more variable, the density, into the equation. So it's another sum of square F test, okay? So basically, we're gonna have, so from 7C, we have the model with these three variables, and now we're gonna add density to the model. So we already have the reduced model. This is the reduced model. I'm gonna run the full model. Basically, we add density to the equation. So we do analyze the regression, linear regression, okay, and then we're gonna do density. Okay, and then you look at the coefficient. ANOVA table, you have the SSR and degree of freedom of the full model in this case, and you do the F statistics one more time, and that's about it. Okay. Okay, so that's pretty much about everything we have in this lab. Okay, so do practice on the extra sum of square F test. It is pretty important. Okay. One more thing to notice is that right now your data set, you don't include case 3. For example, if you want to do your question 3 again, in this case, you actually need case 3. Only for these two parts, you don't need the case 3. So how do you go back? So basically, oh, Siri, I did not count. You do data and then select the cases, and you go back. And you go back, and then in this case, you have everybody. Okay? So that's everything. Okay? Bye.